Hello, everybody. Welcome back to Monte and Carlo Methods. The Mersenne Twister is a hugely popular, efficient, and generally considered good random number generator with a really long period, the length before it's going to start repeating itself, that has been in use for over 20 years. Over the last decade, I keep hearing about the next best thing coming, and indeed there are many new, exciting algorithms out there that might be better, whatever that means. But none of them have managed to dethrone the Mersenne Twister as the default random number generator in almost all scientific computational software packages. It is the default random number generator in Python, R, C++, C#, MATLAB, Julia. I don't think it's the default in Mathematica, but it's certainly an option in there, and it's going to be an option in any scientific programming language you choose, so I think we should talk about it. In this video, we're going to continue and essentially end our discussion about random number generation. While most of this course is going to be mathematically rigorous, this video and the last are just going to be really unsatisfying because they are very, very broad, very not comprehensive overviews of random number generation. This is its own topic. We could spend an entire semester talking about this and still probably not do it justice. And my area of expertise and what I want to talk about in here is what we do with the random numbers we ultimately get. Because they are the basis for all Monte Carlo algorithms, I didn't want to ignore it completely, so I spent a couple of videos on it, but I know I'm not doing it justice at all, so there's the disclaimer. The Mersenne Twister is a random number generator that was first proposed by Makoto Matsumoto and Taguchi Nishimura in 1998. It was named for French theologian, philosopher, music theorist, mathematician, physicist, astronomer, ordained Catholic priest, and general overachiever, Mersenne. Mersenne was a Frenchman who lived in the late 1500s through the mid 1600s. He was considered a polymath, which is a person whose knowledge is very broad and intersecting with many fields, and in a good way. It's not a person who couldn't pick a subject. It's usually a genius who really touches many fields. He collaborated with, or at least corresponded with, scholars in France, Italy, England, and the Dutch Republic, and even he was known in particular for the mathematics of music, and he did a lot of work on our understanding today of the vibrations or harmonics of a vibrating string. As a polymath, he was known for making many connections for very different worlds, and he's known for many things. In particular, you might know him for Mersenne primes. A Mersenne prime is a prime number of the form 2 to the n minus 1. Now, the number 3 is a prime number, and it could be written as 2 squared minus 1, so it's a Mersenne prime. Whereas the number 5 is a prime number, but it can't be written in the form 2 to the n minus 1 because there's no power of 2 that's going to give you 6, so 5 is not a Mersenne prime. Now, this is as far as Mersenne's role goes in the Mersenne Twister. He did not ever study random number generation, but the algorithm by Matsumoto and Nishimura famously has a period of 2 to the 19,937 minus 1, which, as you might guess, is a prime number. So that's how long it goes before it starts repeating. Unlike our horrible sequence in the last video where we generated 0, 1/3, 2/3, 0, 1/3, 2/3. Matsumoto and Nishimura were after really high-dimensional equidistribution. Remember the algorithm ran to you by IBM where they had a random number generator and someone eventually took the numbers and organized them into triplets and plotted them in a 3-dimensional unit cube, and after we twisted it a little bit, we were horrified to discover that all of the points laid on one of 15 hyperplanes. So we're leaving a lot of the cube kind of empty, whereas we would like these numbers to potentially fall anywhere in the unit cube. This was the motivation for the steps taken by Matsumoto and Nishimura, equidistribution. They broke up a 623-dimensional unit cube into very, very, very small subcubes and showed that their generator sequenced with a period of 2 to the 19,937 minus 1 numbers fell equally into each of the subcubes. Now, this doesn't say a lot about randomness, uniformity, or perceived independence of the numbers, but at least we know that we aren't missing out on any of the space. The Mersenne Twister is a bit shifting algorithm, as so many random number generators are. We're going to work with bits and zeros and ones, and we're going to see that lots of things that a mathematician might think of as matrix multiplication can come down to simply sliding bits around, which is a lot more efficient. By the end of this video, I don't think you'd be able to code your own Mersenne Twister, but what I do think you can do is then read any tutorial or the original Matsumoto and Nishimura paper and understand what's going on. As a computer scientist, you'll be already there. But mathematicians, data scientists, physicists, other disciplines, we don't speak the same language. We don't generally work in hexadecimal numbers and things like that. So I'm going to tell you how it goes here. I'm going to give you everything you would need to code it, but probably you'll need to read about it. And I'm hoping this video will help you do that. So binary numbers, these are sequences of zeros and ones. And if we consider having 3 digits, we can write down 8 different binary numbers, 0, 0, 0 out through 1, 1, 1. As I'm sure a lot of you know, these represent coefficients when we look at a sum of powers of 2. So this digit right here is going to represent a coefficient for 2 to the 0. This is going to represent a coefficient for 2 to the 1. And this is going to represent a coefficient for 2 squared. We put those coefficients on and we add them all together. For example, the binary number 1, 0, 1 is going to equal 1 times 2 squared plus 0 times 2 to the first plus 1 times 2 to the 0, which is the decimal number 5. So if you go through this list, you'll get all the decimal numbers. The way I have it ordered, you won't get the order exactly right. This is going to be 0, 1, 2, 4, 3, 5, 6, 7, but you get them all. And by looking at them in this way, we see that we could reduce random number generation on a certain collection of integers to coin flips. If we had a perfectly fair coin that we could flip heads and tails to generate ones and zeros, then we could generate this list in a uniform way where we would get each number 1/8 of the time. And then if we translated them to decimal, we will be generating from the integers 0 through 7 uniformly each 1/8 of the time. So as I mentioned, the Mersenne Twister and so many other random number generators work in binary land with bit shifting, which is very efficient. So let's talk about that shifting a little more specifically. First, I want to talk about a so-called right shift. And this technically is a logical right shift. There are other kinds of right shifts. So imagine the decimal number 23. If I write this in binary, it's going to be 10111. Suppose I want to shift this number 2 digits or 2 bits to the right. If I do that, you can imagine these 2 ones off here sort of falling off a cliff. And I'm left with 101, which in decimal is the number 5. In fact, if we take the number 23 and right shift by 2 digits, we get the number 5. If you want to keep this number to have the same number of digits that you started with, you could imagine filling in the front with 2 zeros. It's still the number 5. This operation is written as 23 with 2 of these right carets and a 2. We right shifted by 2. And if you wanted to do this in, say, Python, it's exactly how you think it would be. You type 23 and 2 of these right carets and a 2. The spaces are not important. I just include spaces for clarity. Then you see that we get the number 5. If you want to do this in R, it's not quite as straightforward. You're going to have to install and load a library first. The library is called bitops, and you're going to have to type install.packages, bitops, enclosed in quotes and parentheses, and then you're going to have to type library, bitops, enclosed in quotes and parentheses. And then to shift the number 23 2 digits to the right, you have to type bit shift R, note the capitalization of the S and the R, open parentheses, 23, 2. And you see that we get 5. And don't forget to close those parentheses. Shifting right by n bits will have the effect of dividing the decimal integer by 2 to the n and then rounding down to the nearest lower integer, like a floor operation. For example, we did 23 and we right shifted by 2 bits and we got 5. If you take 23 and divide it by 2 squared, or 4, you get 5.75. Round it down to the nearest integer below, and you get 5. We have a right shift. Let's talk about a left shift. The number 23 in binary, again, is 10111. And if we want to shift this to the left by 2 digits, we want to push things this way. But in this case, nothing is going to fall off a cliff. These are going to stay right here. And we're going to open up spaces over here in which we're going to put zeros. That makes the binary number 10111 turn into the binary number 1011100. That is equal to the decimal number 92. If you're playing along in a Jupyter Notebook in Python, I bet you can guess how to get this to happen, how to left shift the number 23 by 2 digits. It's going to look very similar to how we did the right shift. And if you're doing this in R, we're going to change the command bit shift R to bit shift L, and note the capitalization of certain letters there. Shifting left by n digits will have the effect of multiplying the decimal number by 2 to the n. So 23 shifted left by 2 digits is going to give us in decimal 23 times 2 squared, which is 92. For the Mersenne Twister, you can think of a binary number of zeros and ones as a vector. I'm going to call this vector x. Now, usually in mathematics, we talk about the components as, say, x1, x2, x3, up to some number. In bit shifting algorithms, when we think of binary numbers as vectors like this, we not only index the components starting with 0, we index them in reverse. So if x is a vector of length w, this will be component xw minus 1, xw minus 2, down to x0. The coefficients for the binary expansion down here are known as the least significant bits, and up here as the most significant bits, which will come into play in our description of this algorithm. The state of the Mersenne Twister at any point in time is actually going to be a whole matrix that's going to be w by n. These are parameters. W is again the word length, which for us is going to be 32, and n is a number that is a parameter. For us, it's going to be 624, which is what is suggested when the word length is 32. I cannot tell you where these numbers come from. I do not know the algorithm that deeply. But again, if you're trying to read about this algorithm, or if you pick up someone's code of the algorithm, you're going to see some constants set up at the beginning of the code. And you should see these numbers if you're working with the 32-bit algorithm. So we start any random number generation algorithm with a seed, just like we did in the linear congruential random number generator. And the seed is going to be a 32 by 624 matrix. And each column is going to represent a binary number. This column is going to be x0, and this is going to be the most significant bit up here and the least significant bit down here. This column is going to represent a vector x1, a vector x2, up to a vector xn minus 1, where n is 625. For most random number generators, the computer seeds the algorithm with something usually grabbed from an internal system clock. And for the Mersenne Twister, that is probably what's happening to grab the first digit, which would be represented in binary here. The remaining columns of this algorithm are filled out with an initialization step of the Mersenne Twister. So once you have the first column of this matrix, you're going to define the next columns through this recursion. So xi with a vector on it is the ith column. And you're going to take the I minus first column and do stuff to it. So what's going on here? There's a lot to unpack. This f is a constant. It is a parameter of the model, much like the a, b, and m for the linear congruential random number generator. For the 32-bit Mersenne Twister, f is actually 1,812,433,253, which is quite large. Now, if you are trying to read about the Mersenne Twister online or in papers or in someone's code, you probably won't see a lot of these numbers I'm talking about today because they're going to be written in binary or hex in a base 16 form, which I'm not going to talk about today, but I am giving you the same numbers. From what I can tell, the parameters in the Mersenne Twister were chosen using a combination of theory and mathematics. as well as empirical observation of the results. I guess, though, I should finish off describing this. This plus sign with a circle is known as bitwise or mod 2 addition. So all these vectors are going to be containing zeros and ones, and your output had better contain zeros and ones. So if you were to add two things and get, say, 5, which you're not, then mod 2, if you divide out 2, the remainder is going to be a 1. So if you add 0 and 0, you get 0. If you add 0 and 1, you get 1. But if you add a 1 and a 1, you get 2, and mod out the 2, that is 0 again. So this is component-wise addition mod 2 or bitwise addition. This, of course, is the right shift operator, and the number of units we're going to shift these numbers is W, the word length, 32 minus 2. And then this is just an index I that increases as you go through the columns. So once you have state 0 for the Mersenne Twister, the seed state or matrix, you want to then produce another matrix, state 1. The Mersenne Twister gives a recipe like this. So there's a lot to unpack here as well. If we call the column vectors of the seed state x0, x1, up through xn minus 1, then xn is going to be the first column of this state. And we are going to get it using columns from the state 0 and operations, obviously. So xn plus k. K here is just an index that's going from 0 to n minus 1. So as you run over k, we're talking about xn, this column, xn plus 1, this column, and so on, going across all columns. To produce the n plus k column, the vector x that goes in there, we're going to grab some column out of the previous matrix. And this is sort of grabbed kind of from the middle. It's another parameter that I'm not quite sure about. I think in the Mersenne Twister, it's around 397, but I will have all the parameters at the end of the video. In general, m is going to be an integer between 0 and n minus 1, so it's going to grab one of these columns back here. Here is, again, the bitwise mod 2 addition. And what's going on over here? Let's focus in on this piece first. Here, I'm taking the k minus 1 vector out of this matrix back here. And there is an L in this superscript, and that stands for lower bits. We're not going to grab the whole column, but we're going to grab some of the least significant bits. In particular, we're going to grab R of them, where R is a parameter of the algorithm. Then we're going to go to the kth column back here, and we're going to grab the remaining W minus R bits and concatenate those two. This line is concatenation to make another vector of length W. This is just matrix multiplication by a matrix A, which is a binary matrix filled with zeros and ones. And Matsumoto and Nishimura chose A so that instead of doing an expensive matrix multiplication computation, we can just get away with bit shifting. Let's check it out. Their A is a W by W matrix. Across the bottom row, we have a vector A, which has components denoted AW minus 1 down through A0. These are zeros and ones. These are parameters of the model. The rest of this first column is filled with zeros, and the rest of the matrix is a block of, it's an identity matrix, a W minus 1 by W minus 1 identity matrix with ones on the diagonal and zeros everywhere else. So let's look at what happens when you right multiply this against a row vector x. This x0, this one bit, is either 0 or 1. Let's look at the case when it's 0. You know from matrix multiplication that you're first going to grab this column and multiply it by this row component-wise and add them up. And if this x0 is 0, you're not going to get that A. It's going to disappear. And in fact, you're going to get 0 for the whole thing because all of these are 0. So our new 1 by W vector is going to start with a 0. In taking the next column of A, we're going to pick up this xw minus 1 when we multiply by 1, and yet this A here is going to go away because we're assuming there's a 0 over here. So we're going to get xw minus 1 on down. If you finish this out, you're going to get this vector, which we can describe as the original x vector right shifted by 1. Now, if you have the time or inclination, you might want to go through this again, assuming x0 is 1. And what you should see is that you'll get the vector x right shifted by 1 and then adding the entire vector of a's. In other words, x times a is going to equal either x right shifted by 1 or x right shifted by 1 plus the vector a, depending on what x0 was. And all of this is mod 2. So if you're adding anything and you get a 2, turn that into a 0. With this, we're avoiding the matrix multiplication entirely, which again can be slow. So thank you, Matsumoto and Nishimura. So we've just described the recursion to get you from state 0 to state 1, and you're going to use the same recursion to get you from state 1 to state 2, and you're going to keep forming these matrices. You're going to ignore state 0, the first matrix, the seed matrix, and the columns of these are representing 32-bit numbers, which could be translated to decimal, which could be your output for random integers, which could be divided by the biggest decimal number that you can get in this form, which is going to be a 32-bit number of all ones. So it's going to be 1 times 2 to the 0 plus 1 times 2 to the 1, etc., up through 1 times 2 to the 31. It's a nice finite geometric sum, which you can show is 2 to the 32 minus 1. So that's the largest integer you could get out of this algorithm. And if you wanted to try to get things uniformly distributed between 0 and 1, you would have to take those integers and divide by 2 to the 32 minus 1. However, Matsumoto and Nishimura noted that they did not get the good results they wanted. They did not get that equidistribution. They actually were missing lots of space in their cube. So they did not give this as the ultimate output of their algorithm, but instead took these states through what is known as a tempering step. Fix that equidistribution problem. The tempering step is to take each vector x, so x, a vector of binary digits, is any one of these columns, and right multiply it by a matrix T, which is going to be a W by W matrix. Now, rather than even attempt to describe this one, I'm going to go straight to the bit shifting, easier way to compute this. What we get is a sequence of operations here. Each column here is a binary vector that I'm going to call x. When we're thinking of the vectors alone and not stacked into the state matrix, you should really think of them as row vectors. So take any one column and organize it as a row vector and call it x. And the tempering operation creates a new vector z through a sequence of steps. It first creates an intermediate binary vector y, which takes x and then does bitwise addition. And we do bitwise addition with of x with x shifted to the right by some number of digits, which is usually called u, which is a parameter. So this is some integer. And then this ampersand is a bitwise AND operation. So over here, I have a vector d, which is another binary vector of zeros and ones. And this ampersand says, take this vector and this vector and look at it element by element and compare the elements. And if both the vectors in a particular element are 1, then the resulting vector will have a 1. And if it's anything else going on when you compare those two bits, the resulting vector will have a 0. So this is a bitwise AND operator. This will create a vector y, which they then mash up again and create a new vector y out of the old vector y by doing a similar operation with 2 new parameters. And then they do it again. And then finally, they create a vector z by taking y and doing bitwise addition with the vector y right shifted by L units, where L is just another parameter. So z is one column of one of these state matrices put through this tempering part of the algorithm. And this is the output of the Mersenne Twister if you're looking for an integer. But if you translate this to decimal and divide by 2 to the 32 minus 1, that's how you get the output of a Mersenne Twister as a uniform 0, 1. For the 32-bit Mersenne Twister, the parameters that I discussed today are all listed right here. It famously has a period of 2 to the 19,937 minus 1, again a Mersenne prime. In the next video, we're going to be doing statistical tests on this or any random number generator that you might be using in your chosen software. So I said we're not talking about random number generation anymore. We're not going to talk about how to generate them in algorithms. But if you have chosen software and a random number generator and you start generating them, how do you know they're good? Are they uniform? Are they appearing to be independent? We know they can't really be independent in an algorithm like this. But as I've mentioned before, they can mimic independence. I smell a chi-squared test on the horizon. I hope to see you in the next one.